Okay, let's start. We've got some things to do today. Mr. Vestal, for Friday, would you please prepare to do the interactive physics demonstrations for Chapter 8? There's one particular one about doing a slingshot using gravity slingshot. Yeah.
Okay.
There's, I think, 2 of them on there. But anyway, the idea is just to explain how it works and also to make a comparison to a binary collision, because it is really a kind of binary interaction. Good. Friday sound okay?
Yep.
Great. Okay, let's see. Let's consider a problem that was assigned for last time, which is I want to consider the force and potential due to gravity around bodies of different shapes. So first, let's consider just a sphere about bodies of different shape. So let's consider a sphere, which we did last time. So you have like the Earth or the Sun, and you want to consider the force due to gravity that would act on some test body that's some distance away from this body. So it's spherically symmetric, as we talked about last time, having a body which is spherically symmetrical, which means, in particular, when I say spherically symmetric, I mean that I can take that body and rotate it, and you can't tell I've done anything to it, right? Close your eyes, I'll turn it some way, keeping the center of mass fixed. And you look again, open your eyes, you can't tell whether I've turned it by looking at the mass distribution, right? That's what spherically symmetric means. Okay, so what is the potential as a function of distance from the center, and what is the force? How do these go in terms of the distance r from the center?
The force is 1 over r squared.
Right, diminishes like 1 over r squared.
And the potential is 1
subtractive.
over r.
Yeah, potential goes inverse with the distance, right? And the relationship between the two?
Is one's the negative in derivative of the other.
Right, the force is the negative derivative of the potential. Now, how can we understand that it goes like 1 over r squared? He explains this in the book in Chapter 8. Somebody like to try their explanation of why does the force go like 1 over r squared? What's his explanation? Remember, he introduces the plana as the mediator, the medium through which this gravity is taking place. So he talks about what is the plana is the surrounding medium in which the Earth is sitting, and the mass of the Earth is then altering the plana that's in contact with it, that is right immediately in the immediate vicinity of the Earth, activates the plana so that it has a field in it. It has this gravitational field present in it. And then that plana that has been altered passes the influence along, so it spreads outward. And this takes place at finite speed, which is the speed of light. That's not something that you know from the understanding of physics, that we're giving you. I'm just stating that fact. Okay, so as it propagates outward, what is the area of the sphere? By the sphere, I mean now the medium that has been altered. Let's look a certain distance away from the Earth or from the moon, from the sun, whatever's the center of gravity. And as it propagates outward, what is the area over which this influence has been spread?
R squared.
Right. Yeah, 4 pi r squared.
Oh,
right? Goes like r squared.
That's so simple.
Yeah. So you're thinning out the influence over a larger area. So the strength of the force is then diminishing, like 1 over the square of the area. 1 over the square of the distance, excuse me. Like 1 over the area. So by the time it gets to this point where there's a test body, the influence will have diminished in strength down to 1 over r squared relative to what it had been before. And so that's why the force on that body, the plana now activated, will now exert a force on that test body back in the direction of the original source. Now, of course, that test body is also emanating its own influence in the plana, which we could use. And of course, it's also working its way back and will exert a force back on the Earth. So the force that the moon exerts on the Earth and the force that the Earth exerts on the moon are both the same, equal and opposite, and they're attractive. Okay, now, using that same argument, same kind of argument, let's suppose we have now a line. Instead of a sphere, we have a very long line. So it's got to be really long. Now, what do I mean by very long? Well, I mean it's long enough. Now we're talking about a distance r from the line, but I want to be far away from either end. So if the line has length L, I want r to be much, much less than L. And then it doesn't matter how close you are to the end. In other words, you're far away from either. I should put r is much, much less than L, and we are near the middle. Line near the middle. In other words, the influence of the ends is negligible. You're just close enough to the center, and you're far enough away from the ends that you don't feel the influence of the ends. So it's a way of trying to deal with an infinite line, but no line is infinite. So it's not really an infinite thing. It's not an infinite. What I mean is no body is infinite. So rather than having an infinite body, you're just very close to a body of finite length. Very close to it, near the middle. Far away from either end. This is not good. This connector is loose over here. It's not good when I'm making hardware changes, hardware repairs. Things have gotten desperate. Okay, don't move it much. Okay, any thoughts about now how will the force and the potential depend on the distance from the line?
Be a direct.
What's that?
Would the force be like straight up like proportional to the distances rather than 1 over the distance?
Is it proportional to the distance? So let's think about it using the same argument now. The mass that's in the line is going to, the body, by virtue of its mass, will influence the plana surrounding the line. So you could imagine the area that's in contact with this is like a cylinder surrounding it. And now as the influence moves outward, the cylinder gets bigger, and the influence is spread out on the surface of that cylinder. So how does the surface area depend on the radius of the cylinder?
What about the volume instead of the area?
So how does
we're
the
taking the ends out. It's still taking the area.
right? And how does the area depend on little r?
Diameter pi.
Yeah, pi times the diameter, 2 pi r. Right? It's going to be the length times 2 pi r. The length remains the same. So how does the force vary with distance? It goes like 1 over r. And again, it's attractive, so I'll put a negative sign there. Diminishes like 1 over the distance from a line. Okay. Well, what does that mean in terms of the potential? The potential, the derivative of the potential is negative derivative of the potential is the force. So what does the potential have to be?
Negative 1 over r squared.
No.
Be 1 over r squared.
Sorry?
Positive.
No.
Wait, so
The
what?
derivative of 1 over r squared would be 1 over r cubed.
Yeah.
So the derivative of what gives you 1 over r?
It's a natural.
Natural log.
Wait, hold on.
Potential goes like natural log. Yeah.
Wait, so the
Is the I thought the potential was the negative.
derivative of the
Right,
force.
so that's why there's a negative sign. Negative natural log r.
If the force is negative, then wouldn't that make the
That would make the force positive due to the derivative of negative ln 1.
What's that?
if you took the derivative of negative ln r and then took the negative of that, you get positive 1 over r.
Oh, I'm sorry, excuse me. Thank you. Good
So-
catch. Okay, so the force near a long line, the gravitational force, because of a long rod, is going to go like 1 over the distance from the rod, if you're far away from the ends. Right? If you get close to the ends, then you got to change this. This doesn't apply if you're near the end. If you're near the middle, and the rod is really long, you're close to the middle, then the force will go like 1 over the distance.
Can you scroll back up?
Yep. Force goes like 1 over r squared.
Oh, okay. I thought it was the other way around.
So
Okay, that makes a lot more sense.
Let's
We're
see.
taking the line to be just.
No, that is right. That is negative there. Yeah. I'm sorry.
We're taking the line to be kind of like one-dimensional instead of.
Yeah.
Okay.
Right. It's kind of really kind of two-dimensional.
Yeah.
Yeah. Because it's how does the circumference of the circle, right? If you take a cross section of this thing, you're seeing increasing circles of increasing, and you're looking at the circumference of that circle. Okay. Anybody want to guess the next geometry I want to do? Done.
What happens when you're near the ends?
Yeah, I don't want to get there yet. Okay, it's just more complicated. In fact, we will study that next term. And what does this have? What we're going to do this when we come back to electricity and magnetism? Yes, because we're going to do these same geometries for electrical charges. We're going to have a charged sphere. We're going to look at the electric field around the charged sphere. We're going to look at an electric field around the charged line, and we're going to look at an electric charge around.
So are we going to be like related to gravity or straight
What's
up?
next?
I said a coiled wire, maybe?
A coiled
With
wire.
certain number of turns.
Yeah, that's not bad. That's not bad. That's not where I was going to go next.
Plane.
What's that?
Plane.
A plane. It's simpler than a coil, right? Let's do a plane.
I meant,
Like a little rope kind of thing.
not the big.
Let's do a plane. So I have a great big plate, huge plate of side L. Great big square plate. Area is L squared. Really big thing. And I want to be near the middle of that plate. And I want to be some distance, let's call it D, above the surface of that plate. And I want to be near the middle, away from the edges, again. Away from the edges, and I want D to be much, much less than D, again. I want it to be a great big plate. You're really close, here's a big plate, and I'm really close to just really close to that plate. I'm far from the edges, right in the middle of the plate. Okay, so how does the force go?
Would it go out to make like somewhat of like a box around it instead?
Well, let's imagine this influence is propagating outward from this plate. Okay, so the influence is propagating outward from the plate. And we're staying close to the plate, right? We're not getting far away from it. We're staying in close to it so we don't have edge effects. So how does the area change? It stays the same. The area is not changing. It's not diluting the effect at all. So if we consider some area, some influence is propagating outward, it doesn't change area. It's not diluting the strength of the effect. So how does the force depend on distance?
It doesn't.
It doesn't. It's a constant. How about potential?
It's like the distance.
Pardon?
Could be zero.
It could be zero. Not
Like
zero. Not zero, because you want the derivative of it to be the force, not the other way around.
Negative D.
It's another constant.
that constant times the length?
Yes.
Negative?
Right. Negative that constant times the distance, d. So it's linear. Potential is linear. It's just a slope, which is a lot like what we see when we're down near the surface of the Earth, right? Near the surface of the Earth, the force is a constant, and the potential is just proportional to the distance. So when you're really close to the surface of the Earth, in other words, this plate could be a piece of the surface of the Earth. And you're really close to that. You're really tiny little dot right here, just a little distance above the Earth. And it doesn't matter that this is a round plate that curves back around on itself. Okay? In the vicinity of the surface, as long as you don't get far up from the surface then. Okay, but in any case, so we have three different cases. The force goes like 1 over r squared, the force goes like 1 over r, the force is a constant. And the potential is either like 1 over r or logarithm or proportional to the distance. Yes, sir? Mr.
So
Best.
theoretically, if someone in Alpha Centauri made an extremely large plate,
Yeah.
then it would have the same pull on us as it did on them.
Yes, if it's much bigger than the distance between us and them. Right? So the distance to Alpha Centauri is 4 light years. So that plate would have to be 4 million light years on the side. You know, right?
That's a big plate.
That's a big plate.
It would have a huge gravitational pull.
Yeah, but it would be the same for us and for them. Yeah.
That is interesting, how that works.
Right. The key in this analysis is that we're not taking into account edge effects. Right. We're deliberately excluding edge effects. And so when he imagines this plate, it has to be a plate where we're not anywhere near the edges. So the distance between us and the plate has to be much less than the distance to the ends of the plate.
So it's like its own galaxy.
Yeah.
It's like a galaxy plate.
There you go. Yeah. The galactic plate.
That'd be
Sounds
one
like
thing
it
to
exists.
You know that you have to rule the universe.
Okay, so notice the conditions on this. We have to be away from the edges, and we have to be the distance from the source has to be much less than any of the dimensions of the plate or the source. Right? You have to be really close to it, in other words. So we're going to you'll see this again next term. We'll be revisiting this when we're going to be doing charged spheres and charged lines and charged plates. You put two charged plates together, what do you have?
You get supercharged. It wobbles.
It depends on the charge.
They might
What's it
compress
called?
and
If you put
stuff.
two plates together that can be charged. What's that? Not quite. We're still doing electrical stuff here. It's a capacitor. You don't know that it's a capacitor. That's why a parallel plate capacitor, although capacitors these days are often made by taking two cylinders, putting one inside of another one. But anyway, we could do the cylinder here. We've done part of a cylinder. We've done one straight line. We could extend the analysis to a line inside of a cylinder. You know, two plates together. You can make a sphere inside of a sphere. You can get more complicated with these things. So you'll see a lot of this next term. Applies equally well to gravity. That much of it does. How the force and potential depend on distance. Okay. Now another thing that we considered in today's homework is the effect of tidal forces. Remember, I said that the Earth, if I have a test body, a little tiny test body out here, has to be small. The force on it depends only on the distance to that body and nothing else. That and the total mass of the Earth. As long as the Earth is spherically symmetric, then the total force acting on this body is going to be proportional to the product of the two masses and inversely proportional to the square of the distance between them. Okay, now, however, let's consider the fact that body, namely the moon, is not a point, but in fact has finite size itself. So let me redraw this thing. And I'm going to take into account the fact that it has some size to it. It has a diameter. Now, the total force is still the same, as I wrote up there. Still the same. Total force is unaffected by that. However, there's a difference in the force exerted on the front as compared to the back, right? There's clearly a difference. The near side of the moon has a greater force acting on it than the far side of the moon because it's closer to the Earth. So there's a difference. Same thing happens. Remember, the moon exerts a force on the Earth. And the force that the moon exerts on the Earth on the nearest side is stronger than on the far side farthest away from the moon. Okay. Now, the total force on the Earth is not altered by this fact that it has a finite radius. I'm not talking about the total force. I'm talking about the difference in the force between the front and the back. If I consider a little piece of it on the front and a little piece on the back, they see different forces. So what happens to the Earth if the Earth is fluid and can deform? Then it will change shape like that. But as long as the moon is going around the Earth, that deformation has to follow the moon. So what are we talking about here? The tides. The tides are determined by the fact that the force at the opposite ends, the force nearest the moon is the strongest, the force farthest away is the weakest, and that produces a deformation in the Earth. The only part of the Earth that really responds to it that's deformable is the liquid part. The oceans deform. Okay, but it also explains something else. Same thing happens on the moon. The Earth exerts a tidal force on the moon, but there's no tides on the moon to speak of in terms of water flowing, but there is an effect on the moon. So suppose that the moon is made out of clay, slightly moldable, not liquid. Then what would happen to the moon because of the tidal forces? It would deform. So the moon would become somewhat deformed. But now if the moon turns, if it's rotating, suppose there was a time when the moon was rotating. While it's rotating, it's now deforming and changing its deformation. In other words, imagine a piece of Play-Doh out there orbiting around the Earth, but it's also spinning. The tidal force causes that piece of Play-Doh to deform, elongated, along the direction towards the Earth, but then it's turning, and that deformation has to be reformed. So what happens if you're standing on the moon is the moon is changing shape constantly. But what happens then if it's doing that? You're deforming it. Something's going on. What happens to the clay?
It gets warm.
It gets warm. It's dissipating heat. It's a dissipation mechanism. So the energy of the rotation of the moon, I'm not talking about the orbiting around the Earth, but the rotation of the moon around its axis, that's being dissipated over time. So what happens? The energy of rotation is being dissipated.
It stops rotating?
It stops rotating. Almost. It doesn't quite stop rotating. It locks in one face to the Earth, right? So that it rotates one time every orbit, so that it's no longer deforming. The deformation is in place and it's set. So the moon would keep one face towards the Earth at all times. That's the effect of the tidal force. The tidal force is the reason that the moon is locked in the way it is. We see only one side, is because of the tidal forces. Over a long time, lock the moon into motion so that it keeps one face pointed towards the Earth. Okay, who's first? Mr. Trimble.
Would the same thing happen between the Earth and the Sun?
Given enough time. Yeah. Now, your homework assignment was to find the size of the tidal force, the relative magnitude of the tidal forces, right? And you find that it depends on the radius here, the radius of the moon divided by the distance between the Earth and the moon. So I should put in the size of the effect depends on the size of the body, the radius of the moon, the tidal forces on the moon. Come on, there we go. Tidal forces on the moon depends on the radius of the moon divided by the distance from the Earth to the moon. Okay?
From the centers?
Yes.
Okay.
Then the tidal force on the Earth, the relative size of the tidal force on the Earth depends on the ratio of the radius of the Earth divided by the distance from the Earth to the moon. If we're talking about the tidal forces that the sun exerts on the Earth, then we're dividing by the distance between the Earth and the sun, which is much bigger. So the tidal force the sun exerts on the Earth is much less than the moon exerts. Except, yeah, no, that's right, in proportion, right? The proportion, relative proportions are that way. Okay, so you have to take those into account. Okay, so this is an example of this process, again, that Rizzi points to in his book, becoming abstract and then becoming concrete, controlling the level of abstraction. So the level of abstraction that we made first was to consider that the moon and the Earth and the planets going around the sun were all like points. We didn't consider the size of them. The Earth is going around the sun, but it's just some tiny little point that goes around the sun, which is a tiny little point. And the moon goes around the Earth. Other planets go around the sun, but we don't consider the effects of the sizes of the planets. So that's an abstraction. So now we go back in and put something more concrete, which is the size of the bodies. And now we get to tidal forces. Without considering the size of the bodies, you would never understand tides. You have to understand that these bodies have size to them. They have extension. And then we get tidal forces. So you can see this understanding becoming abstract, forgetting the fact that these bodies themselves have extension. They just have distance between them. That's the first level of abstraction. Then we get these elliptical orbits, and we understand motion of the planets. Now let's go back and then consider that these bodies have extension, and then we understand tidal forces. Okay, so this is the typical process that we go through in physics, which Rizzi makes very explicit. A ladder, levels of abstraction, controlling the levels of abstraction. So, anyway, these tidal forces you can see the effects of. Where do we see tidal forces in effect in other places in the solar system?
Other moons.
Sorry?
Other moons.
Other moons?
Other planets.
Yeah?
Would it affect the
Yeah.
gas planets at all?
Okay.
Gas giants?
All right. In what way? Where would we see it around a gas giant?
Well, would it affect the various storms on the planet or the way the gas is shifting, perhaps?
Okay, now you're thinking about the effect of those little moons on the gas giants. What about the effect of the gas giants on the moons?
Oh, right.
If the Earth can lock its moon into keeping its face pointed towards the Earth, what could Jupiter do, or Saturn do to one of its moons?
Draw in.
It could actually deform it?
Pulverizes it.
Oh.
The moons of Saturn, the rings of Saturn, are remnants of moons that have come in so close that the tidal forces, remember the strength of the tidal force goes like 1 over the distance to the planet. So the closer you are to the planet, you rip apart the moon, it becomes debris that goes in orbit, still in orbit around the planet.
Rest in peace, Saturn's moons.
Is it, which one? Where is Io? Is it around Saturn or Jupiter?
Which one?
Io.
I
Saturn?
think Jupiter.
Which, is
Wait,
that what they
Jupiter's
figured out? Like,
right.
Enceladus is the one that I see, but they figured out that it has, like, internal water because of the motion.
Because
like,
of the
it's leaving the ice. So they
because
have-
of the tidal forces
yeah.
of the
so
planet
there's
that's in
liquid
orbit,
water, like, at the center of the planet.
keeping it heated. The tidal forces are keeping it heated.
I still don't know that space to live.
I looked it up, too.
Now, Io is a satellite that's close enough to.
I think it's Jupiter.
Is it Jupiter?
That's what it said on the internet.
I think on
Okay. All right. But if you look at Io, it's got volcanoes popping up all over its surface because it's so close to Jupiter that Jupiter is deforming it like a piece of clay. And all that heat that's being deformed, it's causing all the volcanoes, comes from that process of the tidal forces of Jupiter on the moon. So the energy of orbit is being converted into volcanic activity on the satellite. Yes, ma'am?
But if it's always in the same orbit, wouldn't it end up over a period of time deforming it uniformly?
Uniformly.
Well, it would end up still being a circle until it exploded, obviously. But it would be like, if you're deforming something, you're going to deform this way and then this way, and if you keep
It's like putting a ball of clay on a turntable.
yes.
Is it like punching it until you make
No,
like
because when it deforms it one way, when it then deforms it the other way, it like completely deforms it.
It has
It's one of the
first
things that
deforming is
are
not really there.
Yeah, like,
Yeah.
so you ever
As long as it remains deformable. If it somehow it changes its
Oh my gosh, yes.
deformability, then it would get locked in.
If
Probably.
you knock off a hunk of planet, then it's going to obviously change.
Okay, so the final is coming up. What I sent out, everybody should have a copy of last. It's almost last time I gave this final. It should be in your email. Yes? Okay, good. Thank you. There was a couple of blank looks. All right. So use this to study. We'll start today. We'll go through this. There is a question that does not apply. Number 10 is a relativistic question. You won't be seeing any questions about relativity on the final. So the final exam will cover through Chapter 7 plus polar coordinates. Force and potential for gravity near a spherical body. Right? Inverse square law for the force. And also the cause, or the cause and mechanism, cause and medium of gravity, namely the plana, mass and plana. So there are potentially three kinds of mass that we're talking about when we're talking about the plana. When we're talking about the body and gravity, we have the the first one, so-called inertial mass. It's the first mass we learned about in Chapter 3, which is the resistance to the effect of its impetus, right? To the action of its impetus. That's the inertial mass, so-called inertial mass. Now, the two more masses that were introduced in Chapter 8, remember what they are? That's right. That's one of active and passive. The active is when the body acts on the plana around it to activate the plana. That's the active mass. And then when it propagates outward, now its activated plana wants to act on this test body out here. That's the receptive mass. As far as we can tell, they're all three interchangeable. It's just the same. In principle, they could be different. When we study charge, for example, charge and mass are not the same. We'll have an active charge and a passive charge. And those two charges could be the same, but they're not the same as the mass, as the inertial mass. Why active and passive masses are the same as the inertial mass, that's something that needs a lot more thought, a lot more work. In principle, they could be the same. Why are they different? In principle, they don't have to be the same. Why are they the same? Okay? Remains to be understood at a later date. Okay, so anyway, being able to explain this propagation of the influence of the body in the plana from one body to another body, how this mediation works, how gravity works in effect through the plana, and what the plana is. Okay, so in addition to the material up through Chapter 7, then you'll be responsible for those things. Okay, so how about we get started? So, regular office hours on Friday. In fact, I'll even stay there through my lunch hour. Bring my lunch. We'll stay there. So from 10 o'clock until 3:30, I'll be in, except for when we're doing class at 1:25 on Friday. Office hours on Friday from 10 until 3:30, except for class 1:25 to 2:15, when I'll be here. Except for that time, I'll be in my office waiting for you.
With bated breath.
So this exam is just going to start at Chapter 7?
No.
Or 1 through 7.
No.
Oh,
1 through 7.
Through
That's what I was gonna
Chapter
say.
7.
Yeah, I thought
Do we guys know
All
formal definition?
everything up through, including Chapter 7, plus a little bit of
Yes.
Chapter 8.
It's the first question.
Oh no,
What did you
I
add?
can't do formal definitions.
Okay, who can do the formal definition of impetus? Come on.
No, that's mass.
Ability to
The
activate
receptive
power.
impetus
Or
is
no.
No, I want somebody who knows it. Don't give me.
the ability.
I want somebody who knows it. Give me a volunteer who knows it, Mr. Kelly.
The power activated in the body.
No.
The power that,
No.
that activated in the
Just
body
move it
that
in a
moves
linear
it
direction.
at a constant speed in a particular linear direction.
There you go. And the only little part that might be added, the power is what category?
Quality.
Power is a quality. Good. There you go. How about mass?
Mass, the receptivity of a body to its impetus, such that the greater the mass, the less speed.
You're close.
A given impetus, and impart to it a measurement of those first two.
Ah. She's even got the second part.
Jesus.
Formal definition of
No
force.
crime.
What is force? What category is mass?
Category of quality.
Quality. How about force?
The ability of one body to change the impetus of another.
Good. And ability is what category?
Quality.
Quality as well. Right. They're all qualities, isn't that interesting? So what is quantity then?
Quantity extension. But
Extension.
more than-
Simple enough. Quantity is extension. If you-
Quantity.
How much, roughly, how much extension? A body has length, area, volume. Those are all quantities. How about formal definition of kinetic energy? Yes, sir.
The rate of transfer of the intensity of impetus.
Across a distance, I think is what he says.
Yeah, across the distance.
Right. Good. Okay.
No,
Short answers describe the relationship between force, impetus, and locomotion. What is locomotion?
Changing from one place to another.
Yeah, change of place. Right. So what's the relationship between impetus and locomotion?
This causes locomotion?
Yes, the cause of impetus is the cause of locomotion. Why something is moving.
Force imparts impetus on something which causes it.
Great. So force is indirectly the cause of locomotion, but only the indirect cause. Impetus is the direct cause of locomotion. Or another word is proximate. We didn't use it much, but proximate means close by, remote. So force is the remote cause because it's external to the body. The impetus is a property of the body that causes it to move. Good. State the work energy theorem.
the change of kinetic energy of the body is equal to the work done to it.
Good. Does that work? The work of dissipative forces, non-dissipative forces, all forces?
All forces.
All forces. What if I were to rewrite this in terms of an energy conservation or an energy relation involving kinetic and potential energy? Could I rewrite this?
Kinetic initial plus potential initial is equal to kinetic final plus potential final plus work done.
Okay, so let's write the change in energy
Kinetic plus.
is going to be the work done by dissipative forces. Okay, so the total energy there, the work done by conservative forces is expressed in terms of the potential energy, which is in the total energy, right? The delta E there is delta K plus V. So the work done by dissipative and conservative forces, the conservative work gets expressed in terms of the potential, right? So this is the preferred form of the work energy theorem. You can also use it in this form if you're clear that the work there is the work done by dissipative forces, and the total energy is the sum of kinetic and potential. Okay, and you should be clear that the work energy theorem applies equally to dissipative, non-dissipative forces. Indicate whether each item on this list is a substance, a property, a group of substances, or a part of a substance. How about a computer? Group. Bar of gold. The frog. Substance. How about your finger? It's a part. Okay. Let's see here. Standing outside, we're defining a set of vectors outside. X is east.
Oh, we are. Is this window open?
Listen. X is east, Y is north, Y hat is north, and Z hat is up. Facing the sunset, I see that the moon is halfway between the horizon and straight up. I point an arrow 3 meters long at the moon. Write the vector corresponding to that arrow in terms of the unit vectors described. In other words, give the Cartesian expression of that.
The moon's doing things away? What?
No, the arrow is pointing the units.
Oh, okay.
The moon.
Oh, okay. I'm starting to bug out.
Okay, you could write it like this: halfway. The direction is halfway up from west, right? And the distance, the length is 3 meters. You could do it that way, but that's not what's asked. What's asked is to express it in terms of the Cartesian components, the unit vectors described. So, halfway up from west.
-3 over root 2 x hat plus 3 over root 2 z hat.
See, right? So the direction looks right. It's a combination, equal combination of up and west. West being the negative of east. And how about the length of that vector? Let's compute the length of that vector by taking the dot product with itself. So this is 9 over 2 times 1 plus 1. So that's the square of the length. And so the length is indeed 3. Right? So the key there is recognizing that square root of 2 helps to keep the length proper. If you don't put that square root of 2 in there, you get the wrong length. And it's the same combination of keeping the negative sign here is because it's west. Okay? So, how much work would a woodchuck no? How much work is done by a force, constant force? It's the end of the term. All right, here's the. Okay, question here. This is no. Let's go ahead and do this one. Here's the force, and it's a constant force. Note that force does not depend on position or time or anything. Remains constant. And the displacement is equal to this vector. How much work is done on a body that's displaced through a displacement delta r against the force F? How much work is done by that force?
So you have the dot numbers and then.
Okay, so it's 6 plus 9 plus 32. 47. And it should be, remember to put in the units, Newton meters, which are joules, 47 joules.
How you do it so quickly? Oh, okay. Oh, no, yeah.
6 times 1
I thought it was cross-type.
plus
I was like, there's no way she that
no, it's a dot. It's a dot product. So.
I look at, okay, I got it now. That makes sense. Beautiful.
Okay, question though. When is the work equal to F dot delta R? Only for a constant force. So in general, the work, it has to be expressed as a small increment of work over a small distance, dr, an infinitesimal distance. And it's only expressed, as we saw, for example, with a simple harmonic oscillator, the force actually changes with distance, changes with its position. And so the work was not equal to Fx, because that would be kx squared. The work is equal rather to 1/2 kx squared, or negative. Okay? So you have to be careful to recognize that this expression is valid, is the total amount of work done only if the force is a constant. Otherwise, you have to do an integral. You have to start with this form and do an integral, which we will do next term, January. Okay, calculate the torque. So F is 6x minus 3y in. R is 4x meters. Let's calculate the torque.
Cross 7 you have to do y, so it's negative 12. Z at
Joules. All right, should be able to do that. If you need to take it in smaller steps, do so. Notice that the torque has units of energy. Right? Kind of odd. Okay.
Had easy test last.
Sketch the function. Do this on your piece of paper right now. F of t is a times sine squared of omega t. Make a sketch of that function. Does it ever go negative?
Nah.
Yet. As long as a is positive, it never goes negative. Sine squared is never negative.
It's like a good child. It never makes you negative. It's always positive.
So, just to demonstrate that, sine of omega t definitely goes negative. Starts off at 0, goes negative like that, right? And this is 2 pi over omega. It goes from plus 1 to minus 1. And now if you square that thing, it looks like that.
So the period gets halved?
Mm-hmm. Yep.
Interesting.
Mm-hmm.
Is the amplitude the same?
Amplitude is from 0 to 1. So now if I multiply by a, of course, then a times sine squared omega t looks the same, except I just make this a plus a here. Assuming that a is positive, of course. That's what I'd like for a sketch like that, indicating the period of periodic motion, or at least in this case, it's the second time it goes through 0 in the amplitude.
Would you want us to sketch all three to show the changes in each one, or just show how each symbol or each variable affects the thing, like showing the A is the amplitude?
Oh, I'm only interested in the final graph here, but you might want to work your way up to it, on the test, doing this, so you can kind of get yourself there.
I just dive in. I'm the person who dives right into it. I can do this.
You just dive right into the end result. All right, so let's see. This should be a familiar one. I think we just had this, didn't we?
Yes.
On the Chapter 7 test.
Oh, yeah, the yo-yo?
Reverse yo-yo.
Oh,
Reverse yo-yo. Mass M, radius R. It says it's a pulley of mass M, radius R, wrapped around the pulleys along a rope. Assume there's usual gravity acting downward. The pulley consists of a solid disk of uniform density, so that tells you what the moment of inertia needs to be. And I'll give you a table, as before. If I expect you to know a moment of inertia, you can reduce it to looking it up on a table. Okay, you might have to apply the parallel axis theorem to what's in the table, but that should be pretty easy. Okay, so, and then from this you're defined, so we'll do this next class, find the accelerations and the tensions in the rope in terms of little m, big M, radius, moment of inertia. Well, in this case you're given the moment of inertia in terms of M and R.
Does the tension change as the rope unwinds?
Good question. Does it change as the rope unwinds?
Like we did for the homework, do we actually ever take into account that, or?
If the rope is massless, then no. So this would be a massless rope.
So we never have to